Okay, can you all see that?
Yes.
Right. Which screen am I sharing here?
We see your slides in the
Okay, you do see the
edit
slides.
mode.
Okay, okay. I just got confused because the Zoom window moved over to my other window.
Oh, yeah,
Okay.
it happens.
Yeah. Anyway. Okay, so this is presenting on the work that I did last year from winning the 2020 HDEE proposal for integrating the Python and Xarray library in the CDF file format. I presented an update of this, I think, about halfway through the year, and I had mostly completed the CDF to Xarray functionality, and in the last half of the year, I primarily worked on the Xarray to CDF. So I'll just go through briefly, you know, what where the new code is, what the new code does, and then I have some demos prepared with Jupyter notebooks if we have time. Okay, so well, I'll just leave it in this mode, the edit mode. So software to be produced. Basically, what I was going to make was a Python function that takes a CDF file, any CDF file as input, and outputs an Xarray dataset function. I'll talk a little bit more about what Xarray is if you're unfamiliar with it. But basically, if the files are ISTP compliant, that information will be incorporated into the Xarray object. And then also have a Python function that takes an Xarray data set and uses it to output a CDF file. And it will attempt to conform to ISTP compliance, even if there's no built-in ISTP compliance into that data set object. And both of these functions live in the open source library CDF-lib, which is a generic CDF Python CDF file reader and writer. So Xarray, if you're unfamiliar with it, it's an open source Python library, and it is a multidimensional data storage kind of array. They basically advertise it as multidimensional pandas, but it also stores, in addition to the actual data, it stores the dimensions involved in the data. So you can have like XYZ, lat, long, altitude, you know, whatever your dimensions are. And the coordinates of the data values along those dimensions. So you can say, okay, along this dimension is latitude, and you know the first one is 75 degrees and 74 degrees, blah, blah, blah. And it has a strong connection with the netCDF file format. They basically built Xarray to represent a netCDF file in memory. So in fact, there are default procedures in Xarray to load in netCDF files directly into a dataset object and then back out into a netCDF file. So the goal of the project was basically to make a routine that's similar to that, but instead of for netCDF files, use it for CDF files, which is, you know, one of the primary files used in the heliophysics community. One thing I guess I forgot to mention here in Xarray is that they also, in addition to storing these dimension names and the actual data themselves, you can store various attributes, and the attributes just to take the form of a Python dictionary object that can be carried around alongside the data, and you can basically put whatever you want in there. So that's helpful for when determining ISTP compliance or helping with the different routines loading in the data. I'll get into a little bit more about that in the demos later. If you're not familiar with ISTP compliance, it's a dataset standard for CDF files developed by the Space Physics Data Facility. So it basically sets standards on what your CDF file should look like. It says, here are the global attributes that you should have in the file, you know, project name, data version, what mission you're working on, etc. And it also requires specific attributes for variables. So if you have a time series data set, it says something like, oh, you need to have this kind of attribute to say, oh, are you just like a spectrogram? Are you a line data set? You need to have things like what kind of format do you want the data to look like? But perhaps the most important variable attributes are the depend 0, depend 1. These are just the coordinates of the data. So they basically say, okay, depend 0 is the first dimension of the data. What's the first dimension of the data? And it's generally, I think it's required to be under ISTP compliance. It's required to be time always. It's a time series. So depend 0 always points to a time series coordinate. Depend 1, your second dimension on the data set. The depend 1 points to whatever coordinate, if it, like, say it's latitude or something. So you have depend 1 pointing towards your latitude variable coordinate. And basically what I think that this ISTP compliance does is it ultimately makes the files a little bit more similar to NetCDF files. Okay, so what's the end goal of, let's talk about the CDF to X-ray function. What's the end goal kind of that function? It's to create an X-ray data set object that contains all of the information that a CDF file contains. So lossless kind of transition over to what the CDF file has. So basically, to create a single variable from the CDF file, from each variable, we need to obtain the data, the dimension names. So if we can read from depend 0, depend 1, we can read like, okay, what's the time variable? What's the latitude, longitude, etc. And then all of the attributes to that data. And then to finally form all of those variable objects into an X-ray data set, you would need to divide those variables into either data type variables or coordinate type variables. So data type variables are just your, what you're probably going to be using science on. And the coordinates are saying, okay, here's what the time values were for that data. Here's what the latitude values, longitude values. And X-ray data set objects have the ability to have this data and the coordinates right next to each other. And then you can use the data and coordinates to kind of mix and match and perform various functions on one another, like resampling. And then also gather all the global scope attributes from the CDF file and put them into the data set. That's pretty straightforward. And one thing that I noticed, a lot of work, a lot of what I've, ran into trouble with was determining the dimension names and ensuring that dimension sizes are consistent throughout. Because CDF files do not have dimension names by default. So there'd just be some funny behavior where sometimes you could have like a 3-dimensional object, say, in the data set, and then it points to a 2-dimensional coordinate variable, which is kind of funky. And it was just a matter of making sure they all matched up, and X-ray data sets will get really angry with you if your dimensions and coordinates don't match up exactly. So here is, this kind of goes through step by step exactly what it does. I don't know if it's actually worth going through here. My understanding is that the slides will be handed out afterwards. So perhaps one could take a look at all of, what this says. I think it's probably more helpful to go through some examples rather than go through exactly what's going on here. But just at a very high level, it loops through each CDF. It loops through each variable in the CDF file, and it gathers all the data, determines what kind of, oh, is that a raised hand in the Zoom window?
I believe
Yeah.
so.
It is.
Okay.
It's a very, very quick question.
Yeah.
Just say that you convert whatever time data is in the CDF file to Unix or date time. Do you actually properly track leap seconds, because I've seen some people that do and some people that don't. And it's always taken me a while to figure out which packages do and which packages don't. Do you use like CDF's native time conversion? Do you do something else?
Yeah, so if it's in Unix time, it'll convert that to the CDF epoch time, which would use leap seconds. We do keep track of leap seconds that way.
Okay. Thank you.
Yep. Okay, yep. So for each variable in the CDF file, it just kind of loops through and gathers all the data, all the attributes, kind of figures out what the dimensions are of that data, and then puts them into data array objects. It'll figure out which one of those variables is a data, which one of those is coordinates, and put them into the X-array data set object, and then gather all the global scope attributes, and then finally just create the data set object. And then in theory, that should work out fine. So the X-array to CDF, so this is converting the X-array dataset object into a CDF file. This will, once again, these are the kind of the steps. I'll just kind of briefly go over them and you can look at them in a little bit more detail later. But it creates a list of the time varying dimensions. And these will become the records in the CDF file, because that's what ISTP compliance kind of demands. And then it creates a list of dimension variables, which will be the variables that all of these depend 0, depend 1, depend 2 attributes point to. And then it'll take all of those variables, gather all the attributes, all the global attributes, convert the data. So like I was just talking about, it might take Unix time and convert it over into CDF. Actually, what it uses is the TT2000 time units. So instead of CDF epoch, the ISTP standard is actually to use the TT2000. So it'll convert them over to that if the user requires, user tells it to do that. And finally, just generate the CDF file. So I'll go through some examples, like I said. In addition, if a user wants to, they can set up, say like, okay, I want to force this to be ISTP compliant, and give me warnings if it's not. So if you take an X-array to CDF, the X-array to CDF function, and you give it an X-array that doesn't have the correct attributes in that X-array object, it'll start spitting out a bunch of warnings at you. So one of the big things that each data object requires is a var type attribute. So that'll be the first thing it checks, is it says like, okay, you don't have a var type here, so that's no good. If you do have a var type and that var type's equal to data, then it says, okay, well, your depend 0 is missing, so I don't know what your coordinates are. Your depend 1 is missing. Those are really kind of the two biggest ones of the ISTP compliance. But it'll also go through and say, okay, well, I noticed you have this type of variable and you don't have a pointer to the labels, or you don't have the formatting or units or anything described in the attributes. So you need to go ahead and go back and add those. It loops through the global attributes and says, okay, well, I don't know what your project is. I don't know what mission this is. You need to have all that for ISTP compliance. If you're missing a time series dimension, all the data is time series by default. So it'll go through and say, hey, you need a time series dimension. And oh yeah, what I spent a lot of work doing is if your depend 0 or depend 1 or whatever actually does point to a variable, but it has incompatible dimensions with whatever you're working with. It'll give warnings there as well. And then finally, this is kind of random lessons learned that I just kind of jotted down. So while I was going through and testing this ISTP compliance, all this converting an X-ray to CDF, CDF to X-ray, looks like another raised hand. Yep.
Hi, yeah, this is John Vandegrift. Question back on the depend one dimensionality. We've seen some cases where like you think, oh, what are the energies of these spectra? And that you think of it as a one-dimensional thing. But we've also seen cases where you end up with dependencies that you didn't expect. Like, oh, well, the energy for this depends also on the angle. So instead of just having a separate one-dimensional depend one for each, or dependency for each dimension, you actually do end up with a two-dimensional dependency. Have you seen that, and how did you deal with it?
I have not seen anything that depends, like I haven't seen like energy depends on angle. So right now what would happen is it would warn you that that's not ISTP standard, because within ISTP, a data, let me go back a little bit. You can have a two-dimensional coordinate variable, but the first dimension has to be time. So you can have energy bins that depend on time, but you can't have energy bins that would depend on, say, angle.
Yeah, this would be like if you had a, not just an energy spectrogram, but say an energy pitch angle spectrogram. And the pitch angle depended on the energy, or energy on pitch angle, or something where, you know, depending on which energy bin you were in, the set of pitch angles that you had was different. Because you could imagine that happening, right? Where somehow what energy you're at changed the effective viewing piece of your instrument. So those things do happen. They are kind of edge cases. We struggle dealing with that with the happy format. I was just wondering if you bumped into it and if it had solved it.
I haven't actually seen any files that do that exact thing, but what I'm pretty sure it would do is it would all still work and build the CDF file correctly. But if you say, I demand ISTP compliance, it would fail and spit out a warning saying that's not allowed under ISTP. Just because that's, unfortunately, they have a limitation on what you can specify as your depend 0, depend 1, blah, blah, blah.
Okay, I think it was in a CDF. This was, I think it was Maven data in the
Maven,
PDFs, but
okay.
they put it in CDFs. But anyway, we're getting into the weeds. I just wondered if you had seen that.
Okay,
Thank
yeah, I didn't, but I did see a few other funky things that I'll go through. It looks like Ben is also raising his hand. Is that, or is
Yeah,
that Nick from before? Okay.
Yeah, this is actually kind of building off exactly what John brought up. And so I'm thinking about, you know, particle instruments, for example, that have an energy dependence and multiple angle dependencies for every measurement. And you can even have, for example, a physical unit versus a measurement bin unit. And those two things, like if I measure an energy window, that might convert to an energy per charge, but that is both pieces of information are carried concurrently. And I'm wondering how you would handle that.
So you broke up a little bit in the middle there.
Sorry.
That's all good. But I think possibly what you're asking is
and we can also take this offline if you think it's too,
okay,
if it's too in the weeds.
We could do that, but
particle data, representing particle data is difficult because it is highly dimensional and has weird dependencies sometimes. So this is more of like a ISTP CDF thing. But then when you go to transform it, you're probably going to lose something because there isn't really a standard way of capturing it. I think that's the underlying issue here.
The thing I'm running into is I'm actually trying to manually build an X-array data set or an X-ray file from a CDF file, and I end up creating a huge pile of nans as X-array tries to make everything properly aligned, which balloons the data set to the point where it's not necessarily easily handled in memory.
I see.
So yes, there are some edge cases because particle data is hard to handle, but at the same time, is not the point of having libraries that do this to handle those things so everyone's not rolling their own particular thing.
Yeah,
or apart to do stuff and running into problems.
Right. Yeah, I'd be interested in taking a look at one of those files that you're using and see how this would handle it. You know, with like Maven data, the SWIA and SWIA data sets, they are pretty multidimensional with energy, pitch, and angle. So it's like a four-dimensional variable thing, and this handles it fine, but it sounds like what you're saying is that energy also depends on angle and blah, blah, blah. So
Yeah, I'm happy to, we can take this offline. I'm happy to share
Yeah.
with you what I'm working with.
okay, cool. Yeah, that sounds good.
This would be a good white paper for how to improve the heliophysics data environment, a standard way to capture weird particle data.
Okay, let me just go over some brief lessons learned real quick, so that way I don't eat into the time of the other presenter. But yeah, we can take this offline and talk about it a little bit more there. So just really quick, a lot of the files that I've encountered are just mostly, oops, I miswrote this, mostly ISTP compliant. Like they get like 90% of the way, but they always have like a few errors here and there. And I found that interesting. Like sometimes the depend one will point to a variable that's just not there, or it'll contain missing attributes. Yeah, it's all been kind of really interesting to work with. So I can't make the basically what I was hoping was to just have like the CDF to X-ray thing be able to say, oh, this file's ISTP compliant, so don't worry about it, just read it right in. But instead I had to make the CDF to X-ray handle mostly ISTP compliant things as well. And then kind of have a bunch of exception handling saying like, well, it's not ISTP compliant here, so just do this kind of thing by default. Making sure the dimensions lined up. There's this really weird problem. I don't know if anybody else has encountered this, but you can have a NumPy ND array object that's of size 1, but it has no length attribute. If you try and figure out the length of this NumPy array, it says, I don't have a length. And handling that everywhere has been a pain in the butt. But like you can just say, you can go into, Python and say numpy.array parentheses, just like put in the number 1 or whatever. And if you do that, you have a NumPy array object, but it's of length. It doesn't have a length. Just okay. Anyway, so that was a really kind of a pain in the butt. That kept, yeah, exactly, Sean. Yeah, let me just go ahead and start doing a little bit of demo stuff, and we'll see how far we get. Okay, so here's a CDF to X-ray. I'm going to be reading in MMS data, magnetospheric multi-scale mission. You're probably all pretty familiar with that. So this is just a MMS, I think this is magnetic fields. And I'm saying convert all of the time stuff in that CDF file to Unix time, and also take all the fill val attributes and make them into nans. So that's one of the options on the CDF to X-ray function. So let me see. So I'm going to start reading it in. If I remember correctly, it only takes a few seconds instead of being one of these ones that takes like 30 seconds. There we go. So right off the bat, you can actually see there's a little warning here that says, you put this variable epoch state as the depend zero for this variable over here, but the dimensions don't actually match. So that's kind of what I mean by like having this mostly ISTP compliant type files. You'll find just like cases like this randomly in like published data sets. And I guess you just know like, oh, like the people that work with it just know like, well, we know what it does or what it means. But it's just not ISTP compliant. So let's take a look at what that data set object looks like. We've got the dimensions, epoch state. It went ahead and actually created a dimension, which is just called dim0. And it also had to go ahead and create a record dimension, record 0, for this variable up here, because it couldn't find, what dimension that user meant because epoch state didn't match the length. So it had to go ahead and create a new record to handle it. Though, you could probably tell that this data set was supposed to be pointing at this epoch variable here because they're the same length. So you can see all the different data variables here. You can see this variable here depends on epoch as well as this newly created dim0. Different epochs, blah, blah, blah.
So it was just a quick question.
Yep.
This differing lengths, does that mean there are times that don't have data values or what?
Differing lengths, sorry.
This problem you brought up.
Epoch state is too short. Does that mean not
Yeah.
all values have times?
Yeah, so this variable in particular down here, let's look at it. It says the epoch state is its depend 0. So it went ahead and said, epoch state's listed as depend 0, but the dimensions don't really match here because it is actually of length. This variable actually has the length of, whatever this number here is, 1,224,000, blah, 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 instead of this epoch state length here, which is 2,800. So
Probably
even,
a typo. They just put the wrong.
yeah, it's definitely a typo. It definitely, I'm positive it should just say epoch instead of epoch state here. But what the CDF to X-array functionality does is it says, okay, well, since you don't have that depend 0 properly set, I can't really tell what you mean. So I'm going to go ahead and create my own coordinate here, and I'm going to call it record 0. And that's going to be the dimension that this data set here spans.
So there's no time variable?
Correct. There's no time variable in this data set object.
That's bizarre. How can you have a data file that doesn't have a time for every?
Well, it's
quantity?
just one parameter has specified the wrong depend 0, Aaron. All the other ones are fine.
Yeah. So every
Okay, so
other.
This is something you would never get from CedoWeb.
Oh, I don't think so. But it's. I think
It
these
wouldn't
files
work in,
might
it
be
wouldn't work in
on.
CedoWeb.
Yeah, I think these files might be able to be found on CedoWeb. I'm curious how CedoWeb handles it if you try and go ahead and plot this value here. I think the MMS data is on CedoWeb, right?
Yeah, a lot of it is. Most
Yeah.
of it. All.
I'm gonna write down to see what it looks like on CedoWeb.
This is just bizarre.
Maybe someone can try it on the fly real quick. And
Yeah.
seriously, yeah, it'd be interesting.
Yeah, if anybody feels like doing it, it's here, I'll link the file in the chat. Oh, hey, there's stuff in the chat. Okay, X-ray. There's the file name, and here's
Probably
the
just no one looked at this variable before.
I don't know. But that's kind of what I mean by like a lot of the files from Maven, MMS, various things, they all have like this mostly ISTP compliant where like 99% is there, but then there's like always some error like, oh, you don't have the format variable specified or sorry, the format attribute specified for this variable or something like that. So I just linked those in the chat, and yeah, I'm curious to see what CedoWeb does, if CedoWeb has those files.
So I have a question.
Yeah.
Probably not related to the previous discussion,
Mhm.
but can you alter some of the values in a file that you're working with this. So say in NumPy, you might have some 1,000 by 1,000 array, and you can say, okay, I want element 512, 512 to be 10.
Yeah.
Can you do that with this as well?
Yeah, definitely. So you could, for example, take the data out of a CDF, read it into Xarray, and then manipulate the data there. You can just straight up change like a value somewhere, which is what you're saying, and then read it back into CDF. And in theory, you should get the same CDF file, but with just that value changed.
Can you do that without loading like an entire image or something into memory, or do it transparently with an on-disk file without having to have a certain amount of RAM on your computer?
Not with the functions that I've built here. What this does is it reads the whole CDF into the Xarray object, and then it would have to read the whole thing back out. But that's an interesting idea there.
Sometimes I hit the memory limits on my computers pretty hard.
Yeah.
And that's mostly because the kind of the monolithic thing that I'm dealing with is too big for the computer, but there's no reason in principle, I don't think you can deal with it piecemeal. It's just a lot of extra effort if you have to actually implement that on your top level programs. If you have some sort of transparent way of dealing with that, it'd be pretty cool.
Yeah, that's interesting. It'd be great to just maybe read in one variable and then read it back in and edit the CDF file to just change those values. Yeah, that'd be cool. It's just not something that I did here.
So Joe, that kind of capability is possible with Xarray and Dask. And I guess the relevant question for Brian would be whether you've tested whether the CDF compatibility is also compatible with Dask, like the basic Xarray is.
I have not actually tested it with Dask.
So several years ago, I tried doing what I just described directly with Dask, and it looked like it wouldn't let me do it, but it's quite possible. I just didn't know what I was doing.
Gotcha. Okay.
Just to note that you have about 3 more minutes and then we need to move on to Leslie's.
I was gonna say, yeah, I mean, I like the discussion and everything. I just, don't want to cut into Leslie's time here.
No problem. It's been great.
Okay, so I'm wondering what I should pick and choose what to show. Okay, so I mean, that basically sums up the CDF to Xarray functionality. There's some other examples here. And it basically just goes through the different Xarray functionality and says, hey, now that the CDF file's in Xarray, here's fun things you can do. You can plot it, you can select different dimensions, blah, blah, blah. And then I have a different example here with a different file entirely from the Themis mission. But let's just take a look at what Xarray to CDF looks like real quick. And I'll try and go really, really fast. So I'm reading in variable data here. It's really simple, 1, 2, 3, 1, 2, 3, 1, 2, 3, 2-dimensional. And I'm saying, okay, the variable dims have to be epoch and direction. So I'm going to create an Xarray variable. Another Xarray variable that describes what epoch is, what the dimensions are. So this is second 1, second 2, second 3. Create a new variable. And then you just create a data set object with, okay, data is equal to that data variable, and the epoch variable is equal to that epoch variable we just set up. And then what happens if we create a CDF file out of that? So ISTP warnings everywhere. This just was kind of an example to show that, here's all the warnings that it'll give you. It'll say, okay, well, you don't have a var type attribute to describe the variable. You don't have one here. You need a project, source name, discipline, data type. You need all this stuff. You need this variable, you need this attribute, blah, blah, blah. But if you go ahead and add in okay, here's the global attributes. Add the attributes to that data set object, and then go ahead and recreate that CDF. A lot of the warnings go away, but obviously not all the ones that depend on the variable attributes. Let's see, was there something else I wanted to show real quick? Why don't I just, if you're interested, I could send out this Jupyter notebook or post it somewhere. And then one could run through these examples and take a look at it themselves. Maybe I can document it a little bit more so you can see what each one is doing. But what I do at the end here is actually I load in net CDF files, and then I use the X-array thing to load them in, and then I spit them back out as CDF files using just a few different manipulations here and adding things like var type. So that's one of the things that I found I was able to do, is take net CDF files and move them into CDF with minimal effort. Okay, yeah, I'll stop there so Leslie has time. Sorry for going over and not getting through everything that I was planning on.
No, this is great. Thanks, Brian.
Yep.
I'll make sure to include Brian's email in the notes if anyone has any further questions for him about all of this. And I'll ping you separately, Brian, for a link to your Jupyter notebook when it's cleaned up.
All right, sounds good.
Awesome. Leslie, you ready?
Yeah, sure. Let me, well, I can start my video and see if, sorry, I'm sitting in front of a window. That might be
No problem.
not so great. And share my screen. We'll try and do that. I'm just going to share my screen because whenever I pick one file, I always find I need something else and then I'm not sharing it.
No
okay. Slideshow, we'll just go from the beginning. Okay, so this presentation will be less technical than Brian's. I feel a little bad interrupting a good discussion. But I'll just presenting some background information, some intro information on this new project that was just funded this year by the HDEE solicitation. So our goal is to convert barrel data analysis software into Python. Okay, so I'll go on, and I don't know. Okay. So just a little background about the Barrel mission. I'm not sure everyone is familiar with it. So Barrel is the balloon array for radiation belt relativistic electron losses. It was a Living with a Star mission of opportunity to support Van Allen probes. And in this mission, we proposed to launch 40 high altitude balloon payloads in 2 austral summers from Halley Bay Station and Sinai Station, and Halley Bay is the British Antarctic and Sinai is the South African Antarctic stations in 2013 and 2014. The primary objective was to create an array of observation locations to study radiation belt electron loss in conjunction with Van Allen probes. We constructed 46 total payloads, so we successfully launched 40 payloads and then had 6 spares. Just a little bit more about the primary science instrument on board the payload. In the previous slide here, you can, I don't know if you can see my cursor. This is, so these are small packages, hand-launched balloon payloads. And the primary instrument on board the payloads was a sodium iodide scintillator to detect bremsstrahlm X-rays produced by electrons colliding with atmospheric neutrals, electrons precipitating in from radiation belt regions. And this is just an example. So over here in the corner, you can see kind of the core inside of the payload. And this is a little cartoon of the electrons coming in and emitting their X-rays and our balloon detecting them. On On the left here, we have an example of a relativistic electron precipitation event that was detected by one of the Barrel balloons in 2013. So on the y-axis, we're just plotting Barrel X-ray counts per second and time on the x-axis, and you can kind of see this nice big grade enhancement during this time period of precipitation. And so the science goals for the Barrel research was to investigate the physics of wave particle interaction by combining Barrel measurements of electron precipitation with simultaneous spacecraft in situ measurements of waves and plasma measurements and energetic particle measurements. And then determine the relative importance of different classes of precipitation and investigate the high temporal and spatial structure that's been observed in electron precipitation in the past, particularly from balloon observations. So kind of the nice thing about making these observations on high altitude balloons is they're fairly geostationary. And so you get a lot of temporal information from the observations as opposed to a low Earth orbiting satellite, which kind of flies through the region of precipitation. And so our original campaign ran, campaign 1 ran from January 2nd to February 16th, and campaign 2, and that's 2013, sorry, I didn't put the year there. And then campaign 2 started in 2013 and December 27th and ran through February 11th in 2014. And you can see the 2 stations how many balloons we launched here. And so these stations map to a region, to an L value of about 4 and 4.5, which kind of puts us taking off right in the heart of the radiation and the outer radiation belts, which is where we wanted to be. And then with those spare payloads, we were able to have subsequent campaigns, campaigns 3, 4, and 5, and there's actually a 6 and 7 that are the data is being processed for that right now. But campaign 3 was and 4 were flown out of Kiruna, Sweden in August, which was a turnaround time period. So in January and February in Antarctica, you launch and you kind of follow the circumpolar winds around in the circle. You can kind of see the little map of one of the balloon payloads down here in the right corner. And then in the spring and fall, you'll have this turnaround period where the winds are changing directions and you can actually launch and stay fairly locally. So there's a little image over here of the Sweden trajectories, balloon trajectories. So in Antarctica, those balloons were deployed and terminated and were not recovered. Our data was telemetered through Iridium satellite data transfer, not onboard data storage. The Kiruna or the Sweden flights were also, the data was telemetered through Iridium. We had good data connection. We got, I would say 95, 97% of our data down, but it did create data structures that are broken when we went to create our CDFs and stuff like that. So there's data gaps throughout the data, which can sometimes, when you're doing large analysis, be cumbersome to deal with. And then here in the center, you can see this is just sort of a spectrogram plot of our L and MLT coverage. So you can see that we, again, because of that geostationary type orbit, we cover all magnetic local times, and because of the natural drifting in Antarctica, you can get a range of L shell coverage as well. So the average flight time for the Antarctic flights was like somewhere around like 12 days. And then the Kiruna flights were somewhere around 12 to 18 hours. So the Sweden flights were cut down and terminated, and because they were local, we could recover them. So that allowed them to be flown again and again and again, which is great. So again, the objective was to make these electron precipitation observations in conjunction with Van Allen probes. And so here on the right-hand side, I've plotted sort of the Barrel observation binning in color and some example Van Allen probe orbits. And so all of these colors represent are time periods where we are in conjunction with Van Allen probes. And then on the left is sort of a little summary plot of the electron precipitation that was observed by the barrel balloons from campaigns 1 through 5. And so the stars are just electron precipitation, time periods of electron precipitation, and their mapped location in L and MLT. The red stars are those that are in conjunction with Van Allen probes. And then the green triangles are particularly high energy precipitation events, which we would categorize as relativistic. And so you can see that, again, we see precipitation kind of all over the place. But interestingly enough, the higher energy precipitation is mostly in the dusk to midnight time sector. And so there's some really great science that's come out of Beryl. And this is just a slide kind of highlighting some of that. I won't go into too much of the science just because I don't think that's the focus of the group that I'm talking to right now. So you can see kind of just to highlight some of the topics of study that we've been able to quantify electron loss, lots of studies on wave particle interaction, spatial extent and electron loss has been studied on varying time scales, temporal evolution, global coherence scale. So this is all stuff that's meeting kind of those original goals of the Beryl Science campaign. And most of these studies have been individual case studies. So unlike some of the statistical studies you get from Van Allen probes and whatnot, most of the work has been done through case studies for Beryl analysis, but certainly some really interesting and good work there. So the Beryl data that has been produced from campaigns, like I said, 1 through 5 so far, and we're in the works of processing campaign 6 and 7, which I'm not talking about here right now. But all the data format is consistent throughout the Beryl mission. So you have an ephemeris file, you have a fast spectral data, which is X-ray counts per 50 milliseconds and 4 energy channels, a medium spectral data and a slow spectral data. So these are sort of a trade-off in time resolution and energy resolution, depending on what what type of precipitation you're looking at, whether it's a fast precipitation event like a microburst or something a little bit slower like a relativistic precipitation event. And then we have, the usual housekeeping data and some rate counter data, which is an uncalibrated diagnostic data set that we use to monitor the detector during flight. And then on the original Antarctic flights, we flew a magnetometer, though the Sweden flights didn't necessarily have magnetometers. And so that data has been processed into CDF and kind of refined, and we host the data from two locations, the Beryl data server, you can see the URL on the slide, and then CDF web also has the CDF files. And so the original, well, we'll get into the original analysis software in a second. I just wanted to kind of highlight our team that's working on this project. So myself as PI out of Dartmouth College, who just, I have a lot of work with the Beryl data and the Beryl software that exists right now. Our consultant and / programmer is Warren Rexroad. He's our software engineer and will be doing most of the programming on this project. And then we have some unfunded collaborators, which will be very useful. So Michael McCarthy out of University of Washington and Nick and Jim from UC Berkeley, who are our PySpeedS experts. So the original Beryl data analysis software was a part of the original IDL-based SpeedS software structure, if you will, or package. And so we had 2 primary functions. One was a Beryl load data function and a Beryl spectroscopy function. And these 2 main programs kind of utilized all the underlying programming from the SpeedS software package. And so the function of the Beryl load data was to initiate and load all the different types of Beryl data that I kind of showed in that table earlier. And then and you could load multiple data types with one statement call, just to highlight some of the functionality of this, allow for different versions of software, as we were putting out new CDF files and updating things. The program would go and fetch the data from the Barrel server. And this is like one thing that will be changing with the new conversion to Python. But the nice thing about that is it would fetch the data, store it to your hard drive, and then you could continue to use the data offline. And then that data would be converted into T-plot variables for just ease of plotting and kind of looking at the data to see if it had scientific value for the project you were working on. And then we had this Barrel spectroscopy code, which fits a model electron energy spectrum to the observed X-ray energy spectrum through a forward folding technique. And so again, the Barrel balloons observe X-rays, not the precipitating electrons. So you can provide this spectroscopy code a electron spectrum, and it will convert it to X-rays, fit it to the Barrel observation, and then provide back the best fit model to the electron energy spectrum that would produce the X-rays that best fit the Barrel observations. So the package comes with 2 predefined fitting distributions. There's an exponential and a monoenergetic, but you can also fit whatever energy spectrum you want. So there's a user-defined spectrum that can be used with the software as well. So the goal of this project is really to transfer this software capability over into Python as the community moves away from using IDL and paying for licenses and whatnot. We had found that SpeedS had been converted into Python as PySpeedS, and a lot of other missions that were originally under the IDL supported version had shifted over with them. And we thought, well, in order to keep our data relevant, especially considering we're continuing to fly our spare payloads and collect data, it would be very worthwhile to convert over to Python. And our goal is to stay with the PySpeedS family. And so just a demonstration of the functionality of the Barrel load data. So here you can see there's, I've plotted 4 different data values here from Barrel. And so we have, you can plot altitude and L value and MLT location, and then a spectrogram plot. This is probably slow spectrum. And you can kind of see in the slow spectrum that, there's some background signatures here, but there's some periods of enhancement, and this would be the electron precipitation time periods. And so you can then select one of these time periods and say, oh, I would like to know what type of electron spectrum could produce such a signature. And so if we look at this, I've lost my cursor. Come back. So if you look at this enhancement near midnight on August 16th, we can use the Barrel spectroscopy code to kind of take a deeper dive. And so the Barrel spectroscopy code, you can either hard format in the function call what time periods that you want, or it had a GUI interaction where you could select those time periods. So because X-ray background is altitude dependent, you would get an altitude profile so you could see if your altitude was drastically changing, see if some of these enhancements were altitude and background changing enhancements or actually electron precipitation. And you can select your time period of precipitation, and then which is shown here in blue, and then your background time period, which has been selected here in red, and then ask it to run a model. And so here is sort of like an example of the output. This is the output that you get from the Barrel spectroscopy code. And so for this particular instance, I think I'm running a monoenergetic assumption. And so the top panel here is kind of showing you the background X-rays that's being subtracted off in blue and the original observation in black. And then your energy spectrum is in the middle panel where you have counts per keV per second on the Y and energy in KeV on the X. And so here we have the background subtracted observation plotted in red in the middle panel here, and then the assumed or best fit monoenergetic spectrum is plotted in kind of the cyan color. And then the energy range over which the spectrum was fit shows up as the dark part in the spectrum right here. And so you can kind of see how well of a fit that you have. And then the bottom panel is just, again, sort of a graphic representation of how well your fit was. And you'll get a data structure that's returned with all kinds of information. But in this particular case, I fit both. So this example here is for a monoenergetic assumption of electron distribution. You can also fit an exponential. And so that's kind of shown on the right-hand side, comparison of those two, where you can see the difference in the distribution of a precipitating electron distribution as an exponential in dark blue and the monoenergetic, and then how those two fit. And so all these plots were produced from the output of the spectroscopy code. And so you can compare them and decide which distribution you think matches best with the data in your observation. And those types of precipitating distributions kind of give us an idea about what type of mechanism could be driving the precipitation. And I won't go into that with too much detail. And so project goals are to do sort of like a code review of the IDL BDAS version. There are some programs that were created in the IDL version that probably no longer need to be used. They utilize level 1 data, and we're not providing level 1 in our most recent data distribution. And then we'd like to port the data loading functions, the barrel load data over to the PySpeedS package, similarly to how other missions have done it. And our understanding from some initial conversations with Nick is that there's pretty much a template that you follow, and that should be very easy. And I know PySpeedS has their Python version of tplot, so I think we'll be able to maintain that functionality. And then the bigger beef of the project will be spent converting the spectroscopy code over into Python. And we have support from Michael, who is the instrument developer, who has a lot of experience with this developing the spectroscopy code, as well as the calibration and how the instrumentation works, to make sure that that functionality is implemented appropriately and properly. And then just a few other things we'd like to once we've been able to port this project over into Python, we'd like to merge with PySpeedS and just be hosted with them on their GitHub page. And we'll, our proposal highlights, data management plan and some documentation, but obviously would really appreciate the support from this group on what's the best way to implement documentation. And then just in summary, the IDL software was created by the Barrel team to meet the goals of the heliophysics and environment and under the HP data policy. We hope to create data that is openly accessible and scientifically usable. And in order to maintain ease of access to the Barrel data, especially as we continue to collect data, it just makes sense for us to move into the programming world of Python. So very happy to be part of this group and to work on this project, and we look forward to getting a lot of good feedback and information from this group with your experience and knowledge of documentation and testing and archiving. As I said earlier, we have our data hosted at 2 different sites, and our current IDL software pulls from the Barrel data server. This data server is hosted at UC Santa Cruz and is not the most reliable server. It's always going offline, and we're having to put it back online. And so we'd like to transition from the primary location that the community pulls our data is as CDA web. And so there's been well, how do we make that transition? I think changing program languages is a great way to do that. But there's lots of questions. Well, how long do you hold on to old versions of software, and how long do you continue to host from different locations and stuff like that? So I think that'll be discussions to be had in the future. And we've had some internally in our team, but again, I feel like that was a topic that I've heard you guys talk about, particularly in the fall meeting, and would be good to discuss in the future.
So this is Eric from the SpeedS team.
Yeah, hi. We haven't formally met, but thanks for chiming in.
Nice to meet you. So the documentation and the testing that should come along with the template. 'Cause we're actually generating our documentation from the doc strings automatically.
Okay, that's great. Yeah. Okay.
And the testing, we also have the template's also going to have example unit tests, and we also have example validation tests for IDL. Actually load the data in IDL, load the data in Python, and check that the data values actually match.
Oh, okay, great. So if all that functionality is already there, we'll definitely be utilizing that. That's great.
And about the archiving in different sources, we can easily switch between different sources, assuming the directories match. It'll be a little more work if the remote directories don't actually match in the different sources.
Okay.
But the way we're generally doing that is just adding a keyword. And like, for instance, for MMS, we have an SPDF keyword. If you don't set the SPDF keyword, it loads it from the official MMS data center. And if you do set it, it loads it from the SPDF.
Yeah. So, I mean, I think with the new version, and like I said, this will be something that we can discuss further. I think with the new version, we'd like to get away from making the data accessible on that server, because I just don't know how long it's going to be sustained.
So that would be even easier. We just switch over to SPDF by default.
Yeah, absolutely. So I think that would be like our overall goal. It just seems, like I said, a good opportunity to kind of make that transition. But again, how many emails? I mean, it's just going to come down to how many emails do I get? Like, why does this not work? I'm trying to get it from here. So, yeah. And that's all I had.
Awesome. Thanks, Leslie. Any other comments, questions for her before we wrap up? If not, great. I will make sure to link her slides. She gave me a PowerPoint and PDF in the notes for today. And thanks again for presenting, Leslie. And Brian,
Yeah, no problem. Thanks for having me.
Yeah, of course. I think Brian had to drop, but thanks to him for his presentation too.
Yeah.
So yeah, our next telecom will be, I think it's in 3 weeks, February 28th, same time, same place. And we'll hear from some more HDE wrap-ups and intros. So get excited for that. And I'll see you all then. Thanks, everyone.
Thank you.
Thanks, bye.
Yep. See y'all later.